Hi, so this is Christian. I'm a PhD student in Aalborg University, and I'm going to talk to you about my work during my research stay in Mitsubishi, millimeter wave Wi-Fi trajectory estimation with continuous time neural dynamic learning. So first thing is I want to introduce the Wi-Fi localization and tracking problem. So we will try to use is basically reusing the Wi-Fi waveforms for localization and also for sensing applications, so occupancy sensing, indoor monitoring, so on and so forth. But when it comes to localization, mainly we can have two specific or two main groups. So one is frame-based localization, which means like I take one Wi-Fi measurement, frame, packet, whatever feature I'm using, and I have a one-to-one mapping from the object, from the localization of the object and my Wi-Fi measurement. So this is basically just a classification or regression in a one-to-one fashion. Then we have the sequence-based localization and tracking, which is way more powerful. So what we do is we take multiple consecutive frames or packets or measurements of the Wi-Fi, and we are able to regress the whole trajectory. If we take a look into the literature for this, we can see methods that are developed using Kalman filtering for state estimation with a fixed dynamic model, or also when we think about sequence data and supervision, we usually go into recurrent neural networks, but we will show and we will argue how they are not really suitable for the millimeter wave Wi-Fi position estimation task. So then what are the main challenges of millimeter wave Wi-Fi estimation? So mainly there are two: low sampling rate and irregular sampling intervals. So if we think about millimeter wave Wi-Fi communications, we have a lot of beam training in order to do the beam alignment procedure and so on and so forth, but we cannot keep doing that every single time, because this would basically decrease a lot the communication performance, and it will introduce a lot of overhead. So that's why the beam training rate is limited, and this gives us in a sequence of time a low amount of data because of the low sampling rate. The second problem, which is way more difficult to tackle, is the irregularity in the sampling intervals, because of the fact that the user content from the channel compete for accessing the channel. The measurement that we can obtain within a time window are not equally spaced in time. This is actually something that is really a huge challenge that we will try to tackle. And here we can see, for example, an illustration. So we have the robot that is moving with the millimeter wave signals and communicating with the APs. We have in the time window like some irregularly sampled measurements. And then the feature that we will use for our problem is what we denominate as beam SNR. So basically we have all the possible combinations of beam alignment between the AP and the user, and we will basically obtain the SNR for all these combinations. We have a vector, and this is our feature, which is dominated as beam SNR. So here I will introduce our framework that we denominated as neural dynamic learning. So motivated by the fact that we have irregularly sampled measurements, the first question to ask is why don't we try to model a continuous behavior so we don't have to bother about this specific time instance? So that's what we introduce here. So what we have here is that we model the evolution of the hidden states as an ODE, a single value, a first order ODE, that we can parameterize as a neural network, as we can see here. So this neural network, basically as a universal function approximator, should be able to approximate the continuous behavior or the function that then follows this ODE with the input sequence data. So what we have is an encoder-decoder structure, as we can see here. And in the encoder, what we do is that we are able to map the irregular Wi-Fi measurements into a continuous latent space. So we input our BMSNR measurements, we model this ODE as a neural network, and what we do is we encode the input sequence time reversed, because we input from the end, Tn to T0. We input it, we have a neural network that actually maps this into a latent distribution parameterized by mu and sigma. So this mu and sigma basically are parameterizing our input, continuous input Wi-Fi data. What we can do now is that we have also in the decoder side another neural network, another ODE that is modeled by a neural network that provides us a lot of flexibility because we can query whatever time instant. We can take advantage of ODE solvers that are well established in the literature and in general. So then we have like two decoders. And what we do with this ODE is that we can sample it in whatever time instant, as we can see here, and learn what we call a latent trajectory. So this latent trajectory can be Some is supervised by the first head on the top, what we call original waveform decoder. This is basically a semi-supervision over the data that allows us to improve the trajectory learning, but in which we query in the same time instance at the input. And then the second head is what we call the trajectory decoder, basically. So here we can include a lot of supervision. It can be coordinate, velocity, orientation, whatever we want to do. So this is actually really good to enhance the trajectory learning and at the end the trajectory. And here it is presented our loss function. So our loss function is composed mainly of two factors. The first factor corresponds to the trajectory learning. So basically, as we are solving a single on first order ODE, the initial value is really important, which is the set zero that is sampled from the latent distribution is really important. So we highlight it here. And then the trajectory regression, we try to minimize it, of course. And then the second term corresponds to the waveform encoding, the semi-supervision to enhance the learning. So here we can show our evaluation in our experimental in-house test bed. So we have the Wi-Fi's and we have the user that is also moving with a millimeter wave Wi-Fi around in a square trajectory. And we can see here for illustration purposes how if we compare to a one-to-one mapping super vector regressor, the results are not following the continuous dynamics. If we do some RNNs with some tricks to tackle the irregularity, they are not actually being, they are improvement from SVR, but they are not that good. But in the last one, we can see our framework is actually modeling the continuous behaviors being really positive because it's learning like really way more like continuous evolution of the square trajectory here. So to quantify even further the performance, here we show an ECDF of all the compared methods and our method. So the first two, we quantify further with the table. The first two corresponds to the one-to-one mappings method. So super vector regressor, I have one Wi-Fi measurement and one coordinate. I try to regress several continuously. Then the fully connected neural network regressor. So it's a fully connected neural network. We can see that their performance is not that good. Then if we go into an RNN exponential decay and RNN delta T, these modifications, we have an improvement in the performance, but still they had some lacking in the continuous behavior learning, as we saw in the squares. And then here there are several modifications of our framework. So the first one corresponds to the fact that we remove the semi-supervision from the waveform input. Although it's better, we can see that still our framework that was proposed before is the one that exhibits a good performance, like 17 centimeters on average and median 9 centimeters, and actually enhances the continuous trajectory learning. This is basically it. So thank you so much for your attention.